Ya, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. Yeah. We are maybe still waiting for another participant. Yeah. Okay. Anyway, topic for today. This is the last day, last week. Yeah, before we have mid exercise or mid test next week. Just for your information that the mid examinations or UTS covers material from first meeting. I mean, from first week until until today, until this week. So from the definition and signal and system, and then forward to the LTE system in time domain, and then LTE system in frequency domain. And following the schedule, following the study schedule that I already shared at the first meeting, that this week we will have or we will discuss about the Parseval Theorem and time bandwidth product. And then the last section will hands-on using some language programming. Yeah, at the beginning we can use MATLAB or Scilab. The MATLAB maybe some of you already have. Some of you can download from UI, but I haven't checked yet whether the link is still available or not. But for the alternative, we have open source versions of MATLAB. Yeah, actually, this is like replications that developed by the open source, open community that we can call as Scilab. Scilab, it's pretty similar with the MATLAB. Yeah, most of the function is compatible. Yeah. Okay. Anyway, I think all of you already joined this class, so I will share screen actually. Yeah. Okay. I hope you can know the material, the PowerPoint. Yeah. Please for having maybe 5 minutes or 10 minutes to focus on this PowerPoint. I don't want to take you on longer time. So yeah, please be focused on only 5 minutes or 10 minutes for me to explain the Parseval Theorem and time bandwidth product. Okay, ladies and gentlemen, yes, we actually, what is the Parseval Theorem? The motivation is, as we know that when we compute the energy of signal, let's say here is xt. You can see here, this is the xt. This is the arbitrary signal. And in time domain, you can check from the first meeting that when we compute the energy, you can see here, this is the energy, is the integrations, all of the component signal powered by 2. Yeah, this is from minus infinity to the positive infinity. This is the xt powered by 2 dt. Yeah, that's the energy of the signal. And then the problem is sometimes computing the energy signal in time domain is very difficult. It's very difficult, particularly if the signal is complex and complicated signal. So we need to integrate maybe different parts, yeah, with the different functions. So it's going to be complicated. So another way is computing the energy signal from frequency domain. And the Parseval realized, the Mr. Parseval, yeah, Mr. Parseval realized that the energy signal in time domain, it should be equal, yeah, with the energy signal in frequency domain. So you can see here, the energy in time domain is equal to the integrations respect to the time domain with the function of power by 2. And then similar ways, when we already transform the signal xt into the frequency domain, and then we can multiply by itself. It's mean that using power by 2, and then integrate it respect to the limits. Why we write minus infinity to the positive? Because in general, yeah, the frequency domain is from minus, yeah, minus frequency and positive frequency. And please don't forget to put some constant here, 1 by 2 pi. Yeah. So I hope from this slide you can understand that the Parseval theorem states that the energy signal in time domain, it should be equal to the frequency domain. Okay. And then hello. Okay. And then we move forward to the next slide. It's talking about time bandwidth product. Time bandwidth product. The motivation is we can start from the application that from like system design. We want to design a system that in some way should be energy efficient. Let's take a look from the telecommunication system, for example. Yeah, from telecommunication. The problem is how to take an efficiency or energy efficient in this telecommunication system. Actually, the answer from this question is there are many ways to increase the energy efficiency in telecommunication. For example, we can choose the antenna. The right antenna, it means that the antenna with a high gain, so we have receive energy or receive a signal or transmit signal in very efficient. Let's say, for example, like a televisions. When we use only small antenna, maybe moreover place it indoor, so it's harder to receive signal. Sometimes how to improve the receive signal, we put the antenna outside. Moreover, not only outside, but we buy a bigger antenna, expecting that when we have a bigger antenna, it's more receive a signal from the transmitter. Yeah, that's kind of way to improve the energy efficiency. And another way in this case is to reduce the energy of the signal. For example, we want to send some, let's say this is a binary signal. Binary signal, let's say using a voltage, yeah. This is condition 0 and this is condition 1. Let's say something like that. And then we want to send some like a binary 0, 0, 1, 0, 0, 1 like that, yeah. So in this case, we send the signal being like this. In the first period, become 0. In the second period, become 0. And the third period is 1. So you can see here that the energy of the signal is the area under the graph, right? So in this case, the energy is lies at here. You can see here because under the 0 graph is 0 and 0 and this 0. The energy, yeah, energy. We are talking about the energy. The 0, 0, and this is the energy is like durations, the sampling times by 1. Let's say this is 1 volt. So the energy is something like this. Okay. So so it is possible to reduce the time sampling. Yeah, you can see here. Let's say I can reduce the time sampling. So the sampling is only like this and only like this and only like this. So it is possible, right? It is possible. Yeah, it is possible. The information is still 0, 0, 1, right? 0, 0, 1. But here we can reduce because the time sampling here, let's say time sampling 2, this is time sampling 1. You can see that time sampling 2 less than time sampling 1. So in this case, the energy is smaller, right? The energy is smaller. So that's the way, a certain way to reduce the energy. So in this case is reducing the time sampling or reducing the duration of the signal. In this case, you can see here, for example, this is xt. This is the xt, and we have a duration signal here, double TO, 2 times TO. So yeah, so the energy is simply, we can see here the magnitude is 1 multiplied by 2 TO. If this is a voltage, this is power by 2, but it doesn't affect, right? So it's still 1, 2 TO. The effect of the increasing the energy is really depend on the duration of the signal. So how to reduce? What do you think if we reduce the duration of the signal? Of course, the simply effect is reducing the energy, and then so our purpose is achieved. So we achieve our purpose, means that the energy is reducing. But we should consider the bandwidth, the bandwidth of the signal. What is the bandwidth then? Okay. So I hope you already clear relation between the energy and the duration of the signal. So let's talk a lot about the bandwidth. Bandwidth signal, the bandwidth signal is the, let's say, this is the x j omega. It's mean the signal x in frequency domain. So you can see here, this is the x-axis is in frequency domain. The y-axis, this is the frequency signal, the magnitude. Yeah, the magnitude we can write like this, and then we can draw being like this. Yeah, this is actually arbitrary signal. Yeah, this can be. It's mean that the signal have a high magnitude in frequency 0 and decreasing as the frequency increase. Yeah, the magnitude is decreasing when the frequency increase. So the bandwidth is how long or how wide the signal occupies the certain range in frequency domain. That's we call a bandwidth. Bandwidth, yeah. Bandwidth, yeah. It's certain range that the signal occupied, yeah. Occupy. So, what's the problem if the bandwidth, let's say the signal is being like this, or the signal is with changing the color, the being like this. Okay, you actually the red one, the red has a bandwidth. Red is larger than the bandwidth blue and larger than bandwidth orange. Simply like this, right? You can see the white area. Yeah, you can see the red is the largest and the smaller is blue and the smallest is orange. So what is the problem? And then actually, maybe you already familiar with the internet. Many people talk about the bandwidth. What is your internet bandwidth? Yeah, what is the internet bandwidth? But it's different with the internet bandwidth. It's the bandwidth here, we have a unity in hertz. In hertz, yeah, in hertz. So you can see here the bandwidth here. When we have a smaller bandwidth, it means it's better because we can put many information on the smallest area. But when we higher bandwidth means then the system is less effective, because when we have a large bandwidth, it's might be interference to the another signal. Yeah. Jadi sorry, I explain in bahasa. Jadi ketika informasi signal itu ya, informasi itu ditaruh dalam bandwidth yang kecil, artinya itu semakin bagus karena dengan bandwidth yang kecil, bandwidth yang lain bisa dipakai untuk yang lain gitu. Dengan sinyal yang dengan bandwidth kecil, kita bisa menggunakan area yang lain, ini sisanya untuk sinyal yang lain. Berbeda dengan bandwidth yang lebar. Bandwidth yang lebar ini akan menyebabkan interferensi, ya tidak efektif begitu ya, kira-kira begitu. Okay, until this point, is there any questions?
Sir, I would like to ask. From the theory, the Parseval theory, it said that the energy signal in time domain is the same as the one in frequency domain.
Yes.
And you said that we use frequency domain because it can be simpler to calculate.
Yes.
So I would like to know, when is it more appropriate to use the time domain for calculating?
Okay. Okay. After this, I will show you the sum of the signal that it is better to compute in frequency domain rather than in time domain. Okay.
Okay, thank you, sir.
Okay. Is there any questions? Okay. I hope it's clear. The motivation, I mean, the bandwidth problem. And then, okay, let's move forward to the relation between the time and bandwidth product. So you can see the purpose in time is reducing the duration of signal for reducing energy, right? Energy. And the purpose of bandwidth, how to create how to design, like, it's better, design signal in small bandwidth. Ya, udah tahu ya alasannya kenapa small bandwidth, should be small bandwidth, because to to use another spectrum for another information, ya, untuk menggunakan ya frekuensi yang lain untuk apa namanya, untuk informasi yang lain lah. For example, maybe I will extend another example for the bandwidth application. For example, you remember, maybe you know that the FM radio station, the spectrum frequency, the FM spectrum is from 88 megahertz to 107 megahertz, and Prambos is located somewhere, yeah, about the El Sinta is 90 MHz, yeah, El Sinta radio, maybe you familiar, yeah. So if you look at this kind of application, the signal from the El Sinta might be only like this, yeah, only like this in this area. Please imagine if the El Sinta maybe have a wide spectrum or wide signal. So this signal will easily interference to another station radio. So when interference, so you cannot listen the radio clearly. Yes, because there is an interference. So it is better, yeah, to have a small bandwidth. So okay. Okay, and then you already know, and then how to combine these two phenomena, yeah. Once we want to reducing the energy, and then the other is how to smaller the bandwidth. So okay, let's take a look some example here. This is xt in time domain and xj omega in frequency domain. This is xt in time domain, you know, from this graph. Mathematically, you can see here the magnitude equal to 1 when t less than or equal to, yeah, from minus to until to, yeah, the duration is 2 to, yeah, 2 times to. How about the another times is 0? There is no signal, yeah. So then we are interested into transform it to the frequency domain. You can see here, this is a non-periodic signal and continue. So we can use Fourier transform. Okay, please remember, continue and non-periodic using Fourier transform. And then after that, we already compute and we got the result here. The signal in frequency domain xj omega equal to 2 sines omega t 0 divided by omega. And then this kind of signal in frequency domain. Actually, this V is representing the omega, yeah. Maybe yeah, this is the omega as well, and the P is a P, yeah. It's clear, yeah, from this expression, okay. And then we realize the pattern or the graph is like this, yeah. It's like this. You can see here, yeah. Yeah, you can see the signal is likely up and down, yes. Up and down. This is a negative frequency, this is a positive frequency, and this is the peak is at center at 0 frequency, and this point is P divided by TO, and this one is minus P divided by TO or T0, okay. And that's kind of form of signal in time domain and the frequency domain, okay. So you can see here, something like this, yeah. And then I will need your opinion from this graph. Yeah, it's still same graph, and please give your comment, yeah. Please write your comment regarding to the two of the signal. Anything that you get, any information, any understanding about the two graph, please write down at chat box. Please write down at chat box. Anything, any comment, any understanding, any opinion relating to the two graph, yeah, please write down at chat box, please. Yeah, we are I'm waiting. Mempunyai sinyal dalam bentuk seperti ini bisa dalam domain waktu juga loh. Ini kan tinggal diganti T. Misalkan ini bentuk sinyalnya dalam domain waktu. Ketika ditransformasi Fourier, dia bentuknya kotak. Jadi, kalau sinyalnya kotak dalam domain waktu, maka bentuk sinyal dalam domain frekuensi ini seperti ini. Kita menyebutnya signum signal. Kalau signum signal dalam domain waktu, bentuk sinyal dalam domain frekuensinya adalah sinyal kotak. Ya, ini reciprocal lah ya, reciprocity gitu. Kira-kira seperti itu. Okay, so far any question?
Pak, saya mau nanya sebentar.
Iya, boleh.
Ah, berarti kalau gitu yang misalkan yang sinyal utamanya itu kan yang di dekat nol gitu kan, yang di x-aksisnya. Berarti gelombang-gelombang yang kecil-kecil itu jatuhnya noise atau apa Pak? Berarti.
Ini
Iya itu.
atau ini?
Iya atau itu. Iya itu.
Ini sebenarnya apa namanya? Frekuensi-frekuensi lain, tapi dengan energi yang kecil.
Oh, bisa diabaikan berarti Pak?
Bisa, dalam aplikasi bisa.
Selama amplitudenya nggak terlalu besar gitu.
Iya, selama amplitudenya tidak terlalu besar. Betul. Nah, biasanya bandwidth signal itu didefinisikan sebagai area ini, area di mana energi paling banyak itu berlokasi di situ gitu. Ini di rentang, jadi di rentang berapa sih gitu kan? Ini berapa, di rentang berapa sih yang kira-kira energinya itu signifikan gitu loh. Kira-kira seperti itu.
Oke Pak, makasih.
Dan tidak umum apabila mengatakan bandwidthnya segini, itu tidak umum. Karena biasanya ini udah sangat kecil, spektrumnya, energinya udah sangat kecil. Jadi biasanya yang signifikan aja. Begitu juga kalau yang bawah ini, sinyal yang bawah, berarti bandwidthnya ini bagus sekali ini bandwidthnya sebenarnya. Sharp, tajam. Jadi apa namanya, kotak gitu ya. Setelah lebih besar dari frekuensi omega ini langsung ke nol, energinya langsung nol. Itu bagus. Biasanya seperti ini yang kita inginkan begitu. Tapi membuat seperti ini itu susahnya setengah mabok. Kok setengah mabok Pak? Lah iya. Coba bayangkan Anda bagaimana membuat bentuk sinyal yang seperti ini gitu. Bentuk sinyal yang seperti inilah. Gimana? Itu meng-create, mengenerate bentuk sinyal yang seperti ini itu sulit secara aplikasi. Itu lebih mudah mengenerate sinyal seperti ini. Efeknya ya energinya ada yang tercecer di sini gitu, tercecer. Gitu. Oke, any question? Any question? No? If no, we move forward to the exploring MATLAB or Scilab ya. MATLAB or Scilab ya. Okay. Okay, I will share you another screen. So, for example, you already installed the Scilab, so you just open it. Where are you? Oh, ini baru muncul apa ya? Oke. Waduh, I don't know. Okay, anyway. So, I think I already uploaded the PowerPoint for exploring the Scilab. You can open it. Yeah, you can open it. And first, I want to compute discrete time Fourier series using Scilab. Yeah. Allow me to share some screen. Okay, can you see the screen? Yeah. How to compute discrete time Fourier series some signal using Scilab. So, for example, given the xn, this is from infinity to infinity. So you can see here the magnitude is 1/2, 1 minus 1/2, 0, 0, 0, 0, 1/2, and 1. And you can see this is a periodical signal. Why we can say periodic? You can see here from 1/2, that is 1/2. So yeah, you can take one periodic. So the xn is a periodic with n equal to 5. Why 5? Yeah, this 1, 2, 3, 4, and 5. So, and then the problem is compute the xk. Xk means the signal in frequency domain. So the Scilab solution, first we write the comment like this. So we input or write one period, the xn, let's say 1 minus 0 0.5, 0, 0, 1.5. And then the xa, the signal in domain frequency, you can see this is using syntax FFT. This is FFT, this is fast Fourier transform. Yeah, the input is xn divided by 5. This command is to transform signal from domain times to the frequency domain. Yeah, and then we can plot. Yeah, if we want to show the xn in magnitude, yeah, and this thing is plotting the phase. Okay, and using this, actually we are practicing the from the PowerPoint. If you look at the PowerPoint page, what page? Wait a moment. Forget. Wait a moment. And the FS. Please open a PowerPoint at page 11. Page 11, yeah, page 11. Okay. I can show you the page 11. Okay, yeah, you can see now on the page 11. the example 3.2, example 3.2, please determining the discrete time Fourier series coefficient. Yeah, means that we have to transform the signal from times domain to frequency domain from figure 3.5. You can see here figure 3.5. This is the xn. You can see the xn is periodic. You can see the periodicity, for example, from 0, 0 is 1, 1 is minus 0.5. It's correct, yeah? And then being 0, 0, and then 1.5, yeah? And then 1 again. So in this case, we take the 1 period. So the 1 period is n equal to 5, right? Okay, correct, yeah? And this is a Fourier, this is a periodic signal. Periodic. Because this periodic and discrete, yeah, periodic and discrete signal. So the method that we have to use is using discrete time Fourier series. Ya, analytically menggunakan analisis atau menggunakan cara konvensional dihitung ya. Nih, mencari XK-nya adalah ini rumusnya. Actually the formula is wait a moment. The formula is like this. Yeah, you can see here. If you remember that this is how to compute from time domain to the frequency domain, and that's the formula. And then we move forward. You can see here, this is the way of computing, the way of transforming from time domain to frequency domain, blah, 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 using formula, something like this. And then we got the result. Then we got the result for x equal to minus 2 until x 2. Or in another way, when we use n from 0 to n equal to 4. Yeah, total is 5, right? 5, 0, 1, 2, 3, and 4. Total is 5, 1 periodic. How about this one? This one is same, minus 2, minus 1, 0, 1, 2, also 5. So it's another method. This is, you can use this one, and also you can use this one. This is will have same result, yeah. And then we move forward to the result, yeah. Yeah, this is the xk in magnitude, yeah. And this is the phase of xk. This is the phase, and then you got because this is the periodic, so the magnitude is also periodic and the phase also periodic. So we want to compute this one using Scilab. Okay, we want to compute this one using Scilab. So back to the PowerPoint here, you can see actually this is the syntax or comment using Scilab. So now I would like to demo using Scilab. So you can see this is the interface of the Scilab. You can write directly using command line. For example, the xm, and it is equal to 1. This is 1 period signal, minus 0.5, 0, 0, and 0.5. Okay, you got this? Okay. This is actually the xn, yeah, the xn. And then we want to compute the xk. Xk is actually FFT xn, yeah, if the input is xn divided by 5. Why 5? This is because the one period is 5. So we got this one, okay? This is really in the signal in frequency domain. Yeah, you can see, yeah. This one 0.2, this is a complex number actually. And then we want to plot, we want to compute the magnitude component of xk. So we can, let's say the magnitude of xk, we can write like this. And then the comment that we use is absolute of xk. Okay, this is the absolute of fk. And the magnitude, and then we want to plot, let's say, let's plot it to check whether it's correct or not. So from 0, the incremental is 1 and until 4, and point magnitude, the input magnitude xk. Okay, something like that. Okay, let's see. Okay, you can see here. Yeah, you can see here, yeah. If you compare to the result from the PowerPoint, wait a moment. Okay, how to say? Okay. Sniff. Okay, I want to sniff it, and then okay, I want to sniff this one, and then I want to compare with the actually. The PowerPoint, right? This one. Can you see the both graph?
Yes, sir.
Okay, okay, let's take a look. Which is correct or not? Actually, this one is 0.2, right? And for the next, it is around 0.275. Okay, and this is 0.235. Also this is a similar, and this one is 0.275. Yeah, if you look at this one, this point is equal to this point, 0.2, right? And this one equal to this one, this one equal to this one, this one is equal to this one, this one is equal to this one. Okay, is that clear? Can you see?
Yes, sir.
Yes. So the result is same, right? So you already know another the simplest way to calculate. You no need to being maybe complicated. Yes, using Scilab, and then you got the result. But yeah, the limitation of the Scilab, you can only use for discrete signal. How about the continuous signal? Totally no. Unfortunately, yeah. Okay, yeah. For the magnitude case, solve, and then for the phase of xk, let's okay. So back to the Scilab. Yeah, Scilab, where is my Scilab? Okay, share. And then we want to compute the phase of xk, right? Phase of xk is the phase actually is inverse tangen in Scilab using command atan the imaginary part of xk, right? Yes, because the complex number is consists of imaginary and real, and then real component of xk, and then done. Okay, this is a phase of the what? Of the xk phase, yeah, phase, and then we want to plot again. We make array sum for the x-axis incremental, so you can like this, and then of phase of xk. Yes, it's very simple, yeah. And then just plot it. Yes, you got it. Yeah. Okay, let's check together. Yeah, let's check together using okay, comparing with this result with the results from the PowerPoint. Yeah, let's take a look. This one. Okay. Can you see now? Yeah. Okay. Okay. You can see. Wait moment. I have a technical problem. This one. And then this. Okay. And then we want to share this one. Okay, this one. Okay, and then make an annotation. Yeah, you can see here, this is 0. And this is around, yeah, less than 1 lah, yeah, less than 1 is equal to 0.76. And this is around 0.53, yeah. Yeah, according to the computation result, yeah, from Scilab. And this is minus, right? Because this is a 0, so it should be minus 0.63. This is it should be minus 0.76. So this is the you can see here, this is 0, actually equal to this point, and this one, this point, and this one is this point, and this one is this point, and this one is this point. Okay. Okay, it's clear, it's same. So we already proved that Scilab is powerful. So you can easily compute the magnitude and the phase of the signal in frequency domain. So any question? So any question? No question? No question. If no question, we move forward. Yeah, move forward to the what? to the what? Where is my PowerPoint? Okay, you can see now how to inverse. Inverse. Yeah, inverse is very simple. It's just using IFFT. Yeah, FFT multiplied by 5. Why this is multiplied? Because at the first we divided by 5. Why by divided by 5? That's based on the formula, right? We should have divided by 5. Yeah, by not by 5, by the periodic. Yeah, divided by the periodicity. Yeah, it's periodic. Yeah, and that's why when we inverse, we should compute multiply by its periodic. Yeah, so yeah, it's very simple. So let me show you using a Scilab. Yeah, again. You can see here. So just write the inverse of xk, right? Inverse of xk just IFFT. Oh, sorry. Too smart. IFFT and then what? Just write the xk multiplied by 5 and then bam, we got the answer just equal. Yeah, you remember? Yeah, this. Yeah, it's just this equals this one xn. So inverse xk is equal to the xn. Yeah, very simple. Yes, very simple. And then here. Okay, any question? No question. No questions. Very simple. And then let's move forward after inversing, and then how to inverse discrete time Fourier transform. Yeah, please remember that why we using a discrete time Fourier transform, because the signal is non-periodic and discrete. And again, you can see here. Oh, wait. I think I'm not share the screen with you yet. Okay, right now I already show you. This is the inverse, and then we move forward how to compute the discrete time Fourier transform using Scilab. And you remember that using this method, if the xn is non-periodic and discrete. Yeah, discrete. Yeah, of course, the signal should be discrete and non-periodic. You can see this is non-periodic. Non-periodic, yeah. There is no another infinity in the left side, and there is no infinity in the right side. So the signal is only located in this point. 1 minus 1/2, 0, 0, and 1/2. And this is not this is not periodic. Yeah, remember, this is not periodic. But if I come write like this is a periodic. It means that in the left side here there is a signal. In the right side here there is a signal. But if I write like this is only this in this location. Okay. Any question? No. So in this case, no need to compute the periodicity. So it should be deleted. Yeah. So should be deleted. Yeah, this one should be deleted. Yeah. Should be deleted. Yeah. And then find the xk. It means the signal in frequency domain, and the solution using Scilab is, you can see it's pretty similar. It's pretty similar, but you can remember, maybe you can notify there is no divider here. No divider by the periodic. It's periodic, no, because there is no periodic, so no need to divide by its periodic. So something like this, and then the result is yeah, something like this. Yeah. Why this is maybe which one? And you can see here that the total how to say, total sample is 5. Yeah, for example, this is total is 5, so that's why you can see here the result will be same with the previous one because we pick up this one. Yeah, same. Okay, any solution? And this is the inverse of discrete time Fourier transform. Yeah, it's similar, but again there is no multiplier. There is no times with the periodic. No. That's, yeah, simple. Okay. Okay, any question? Any question? No question? Yeah. No, if no question, ya sudah. Yeah. Are you ready for the midterm test? Okay, that's all the material before the midterm test. So the UTS will cover until this topic. So it's time to discuss about the UTS or midterm test. So, any question related to the UTS? No.
I would like to ask, sir, maybe regarding the midterm test, the mechanism, like how will it be conducted, and is it conducted on the normal class time?
Oh, you mean offline?
No, I mean like the time, the like usual class, like
on the exact time, like duration and
yes.
I see. I'm not decided yet because I have to coordinate with another lecturer with same subject, yeah, like Pak Aris or Bu Mia, Prof Dadang, begitu ya, that they teach same subject. So what kind of examination will behave? I'm not decided yet, but later I will let you know, maybe in this week or yeah, at least in this week.
Okay, thank you very much, sir.
Yeah. Is there any question? Yes. Bobby.
For the one that you sent on the group, the UTS is from previous year. Do you have the answer for it, sir? So I can check it.
Answer, yeah. Yeah, actually I have an answer, but I think at campus, yeah.
Oh, okay, sir.
Yeah, at campus, and yeah.
Okay, sir. It's okay.
Yeah, you can exercise by yourself or discussing with your friend, or maybe you already exercise by yourself, and then we can discuss right now.
Oh, no, not yet, sir. I haven't done
not
it.
Yet. Okay.
But if I have done it and I want to ask question, is it okay if I just
yeah,
put
it's
it in the
okay.
group?
It's okay. Please post it at group, yeah.
Okay,
so
sir.
everyone can
Thank you,
know. Yes. But maybe little information about the UTS, yeah, it will be open book, open all, and except open your friend. And yeah, Please, yeah, I expect you very much to conduct by yourself, so it's not cheating. Yeah, in this era, cheating is very easy. Yeah, very easy. Actually, I don't want to tell you the way because we'll be inspiring you. But yeah, please, I expect you very much to conduct by yourself, because yeah, it is to measure the real score of you, the real understanding of you. Okay, maybe we still have 1 hour. Yeah, do you have any question, any comment, or maybe any material that you feel not really clear? Yeah, you can ask now. We can discuss and make a solution. Okay, one information. According to the guideline, I mean the SAP, this week I should, this week I should give you homework for group works, but I consider to cancel because I hope you can focus on your preparing the UTS. So I will change the group homeworks to the next after UTS, yeah. But the topic, of course, different.
Actually, sir, if
yes.
you want to give us a homework, we are happy to do it because I think it helps us to understand. But
Not homework, not self homework, but like a small project actually. And this project
okay,
is
sir.
maybe not will be not evaluated at a mass. It's like improving your skill to use the Scilab. Yeah.
Okay, sir.
Yeah. So if you read the guideline, I mean the SAP that I show you at the first, you can see there is will be 2 times of group works. First before the UTS and another is after UTS. Yeah. And this group work is actually improving the skill of using a software, not analytically. But for the UTS is analytically. But you can use the Scilab if you can check the answer, maybe something like that. The exercise, maybe if you are interested in an exercise, I will let you know that first what you have done in self-assignment, please take it yours time to understand more, and then about the transformations, you have to open the method of transforming from time domain to frequency domain, including Fourier transform, Fourier series, the Fourier discrete time Fourier transform, and discrete time Fourier series. Yes. Please open again material from the engineering mathematics. Or you can ask right now what kind of problem, maybe from PowerPoint or another resource, so we can discuss. If no question or we no material that we want to discuss more, so we finish our class today and prepare your UTS. Yeah, next week. Yeah, study hard and what to say? Yeah, prepare not only for this course but all course that you take. Yeah, and then thank you very much for your attentions and see you next week for having UTS. Yeah, stay healthy and eat health. Yeah, thank you very much. See you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Thank you very much, sir.
Thank you very much, sir.